Welcome to lecture 6.3 covering logarithmic functions. Now, if you recall in 6.1 and 6.2 we were dealing with exponential functions, and before we dive into this, I'll just let you know that logarithmic functions are the inverse functions of exponential functions. You will definitely want to have your calculator handy for these next couple, or next few rather, lessons, because you will be using it to calculate logarithms. So we'll go ahead and jump on in. Okay, so the first thing we want to look at, since we know that exponential and logarithmic functions are inverses of each other, we want to look at how to convert between the two of them. And that's going to really help us understand the definition itself of a logarithm. But we'll start with an example to kind of see why knowing how to work with logarithms is even useful to us. And this is just one of many examples that we could use. So we'll start with this example. The Richter scale is a base 10 logarithmic scale. In other words, an earthquake of magnitude 8 is not twice as great as an earthquake of magnitude 4, but rather it's 10 to the 8 minus 4, which is 10,000 times greater. So in this lesson, we're going to look at the Richter scale a little bit more and base 10 functions, and just logarithms in general. So in order to analyze the magnitude of earthquakes or compare the magnitude is just a measure of the greatness of that earthquake, how big of an area it affects, as well as how hard it hits, if you will. So to do this, we have to be able to convert between logarithmic and exponential forms. For example, suppose the amount of energy released from one earthquake were 500 times greater than the amount released from some other earthquake. We could say then, or we could calculate this magnitude by solving this equation. 10 to the x is 500. So if I know it's 500 times greater, that had to equal some power of 10 on our Richter scale, or using our Richter scale as a way of measuring the magnitude of it. So x represents the difference in magnitude. So just like we did here, we subtracted magnitude 8 by magnitude 4. So the difference in magnitudes on the Richter. So I'm going to change color so I'm not writing in pink the whole time. How would you solve for x? Well, so let's take a look at this. 10 to the x equals 500. So basically this is asking us, what can I raise 10 to get 500? So 10 to the first is 10. 10 squared is 100. 10 cubed is 1,000. So it's somewhere between 2 and 3. So we could give an estimate of that value. Then it would be nice to have a way to algebraically pull that exponent down into the realm that we like to work in, the numerator of the fraction, and be able to solve for it. Now, we could also use a graph. We learned this in 6.2, I believe. I can't remember if it's 6.1 or 6.2, about how to use two graphs to solve an equation. So we'd We do y1 equals 10 to the x, y2 equals 500. So I have this 10 to the x, this exponential function equaling this horizontal line, y equals x, and at an x value of it looks like about maybe 2.6. Those y values will be equal, and that value that they're equal at is 500. But obviously this is not the best way of going about this, because I can guess that that's about 2.6, but I really need to be more precise than that. So estimating from a graph is imprecise. To find an algebraic solution, we have to introduce this new function, this inverse of the exponential. So observe that this graph off to the left, this exponential function, it passes the horizontal line test. In other words, I can put a horizontal line anywhere on that exponential function and it will only pass through one point. That means that an exponential function is 1-to-1. And so it has an inverse that is also a function. We learned that a while ago. I believe in section 3.7 we learned about inverses, and I want to say that that was module 2. As in the case with all inverse functions, we simply interchange the x and y and solve for y to find the inverse. So we simply interchange x and y. Okay, so to represent y as a function of x, we use the logarithmic function, and I'll write this bigger at the bottom, y equals log base b of x. The base b of a number is the exponent by which the base b logarithm, sorry, I had to think there for a moment about what that blank was. The base b logarithm of a number is the exponent by which we must raise b in order to get that number. In other words, what this tells us is if I raise b to the y exponent, it will give me x. So in a nutshell, this is giving me that answer of b to the something equals x. And that's how you interchange between logarithms and logarithmic functions and exponential functions. So that's all that this is telling you up here, is that when you have log base b of x is y, that's the same exact thing. That little double arrow says if and only if b to the y equals x. And don't forget, b has to be greater than 0 and b cannot be 1. That's from the definition of our exponential function. So I always point out to students, when you are converting from logarithmic function to exponential function, you start at the base, raise to the is, and I'm calling that the is because you can replace an equal sign with the word is. So start at the base, raise to the is, and that equals the of. And the reason I say the of is because the way we state this in English language is log base b of x is y. Okay, so my little hint that I give students is start at the base, raise to the is, and that equals the of. Start at the base, raise to the is, that equals the of. And all that information is given in textbook speak in this gray box right here. So I won't go through that gray box again because we've pretty much addressed all of that. Okay, can we take the logarithm of a negative number? So let's think about this for a moment. Let's say I have log base 2 of, I don't know, negative 8. So what this is asking us, and that equals, I don't know yet. I got to think about it. So this is asking us, what can I raise the base 2 to equal negative 8? So let me just rewrite this. 2 raised to the something equals negative 8. So think about this for a moment. Is there anything, any value that you're ever going to be able to raise a positive base to that will give you a negative number? And the answer is no. Even if I raise that to negative 1, that creates a fraction. That's 2 to the negative first power, which is equal to 1/2. Or 2 to the negative third power is equal to 1/8. It's not equal to negative 8. So the answer to that question is no, because a base of an exponential function is always positive. So no power of that base will ever result in a negative value. And I thought that was very important to point out to you. So how do we convert into an exponential form from a logarithm? Well, all you do is rewrite it as b to the y equals x. You start at the base, raise to the is, and that equals the of. So on the left-hand side here, 1a starts out with log base 6 of the square root of 6 equals 1/2. And if I want to convert that to exponential form, that says, I start it, let me get a different color here. I start at my base, raise to the is, and that equals the of. This says 6 to the 1/2 power is equal to the square root of 6. So I've converted to exponential form, and that's a true statement. Because remember, rational exponents, a to the m over n is equal to the nth root of a to the nth power. Okay, 1b on the left-hand side, I have log base 3 of 9 equals 2. Once again, I start at the base, raise to the is, and equal the of. So this says 3 squared equals 9. And we know that to be true as well. Let's look at the right-hand side just to practice a little more with converting here. So 1a on the right-hand side starts with log base 10 of 1 million. And there's an important concept embedded in this little problem here. And I'll tell you in just a second what that concept is. Start at the base, raise to the is, and equals the of. So this changes form into exponential 10 to the 6th equals 1 million. Okay, let me point this out to you because this will be very helpful for you to remember. Whenever you have a power of 10, so you have 10 raised to some exponent, you don't have to put that into your calculator because it's always going to have the same amount of zeros as the power that you've raised to. So 10 to the 6th is a 1 with 6 zeros. that's 1 million. So that's a very handy little piece of information to keep in your back pocket. So you don't have to grab your calculator every time you're doing base 10. Okay, so 2b here, log base 5 of 25 is 2. Start at the base, raised to the is equals the of, and we end up with 5 squared is 25. Okay, now we're going to go the opposite way. We're going to start with exponential equations and turn them into logarithmic form. So 1a starts with 2 cubed is 8. We start at the base, raise to the is, and that equals the of. So log, same base here, start at the base, raise to the is, and that equals the of. Okay, 2b, 5 squared is 25, log base 5 of 25 is 2. 3c, 10 to the negative 4th power equals 1 over 1, 2, 3, 4. I didn't even have to put that into my calculator because I know it's going to have 4 zeros there. So start at the base, log base 10, raise to the is, and that equals the of. So negative 4. So that says, just to remind you, that says 10 raised to the negative 4th power is 1 over 10,000 there. All right, same thing, just a couple more practice problems here. It doesn't hurt to practice this, and really it's just a matter of remembering the definition. So log base 3 of 9 is 2, because 3 squared is 9. 2b here, 5 cubed is 125. Log base 5 of 125 is 3. And 3c, 2 to the negative 1st power is 1/2. And that is because log base 2 of 1/2 is negative 1. Okay, so evaluating logarithms. Knowing the squares, cubes, and roots of numbers allows us to evaluate many logarithms mentally. It would be beneficial for you to just, learn perhaps the first 25 squares. So when I say that, I'm talking about, okay, 1 squared is 1, 2 squared is 4, 3 squared 9, 4 squared 16, 5 squared 25, all the way up to 25 squared. 25 squared is 625. It would benefit you to just memorize those. And you probably don't need to memorize as many cubes, but it would be beneficial as well to know a handful of those, at least up to 5 cubed. So 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, and 5 cubed is 125. But the reason that this is helpful is because you can do things very quickly in your head without having to grab a calculator if you know some of those basic squares and cubes and their corresponding roots. All right, so given a logarithm, to evaluate it mentally, you can rewrite it in exponential form. I like to set up the question that it asks, and that's the second thing that they mentioned there, to what exponent should b be raised in order to get x. So if I look at this first example here on the left, remember you start at your base, raised to your is, and that equals your of. Basically, this is saying, what can I raise 4 to make 64? And in that case, 4 would need to be cubed, so my question mark is a 3. Okay, same thing here, right next to it. What do I raise 121 to make 11? So 121 raised to something equals 11. I'm raising a value to an exponent, but getting a smaller number. Whenever you see this situation happen, the first thing you should check for is a root, because we know we can write roots as rational exponents. I'll remind you again, a to the m over n is equal to the nth root of a to the nth power. And because I know my squares and my square roots backwards and forwards, I know that 11 squared is 121. So if I take the square root of 121, I get 11. But I can't raise to a square root. That's not how you write that. So question mark here is 1/2. So when I raise 121 to the 1/2 power, I get 11. That's because that's the same thing. That 1/2 power is the same thing as the square root of 121, which is 11. Okay, so bottom left here, start at the base, raise to the is, and that equals the of. Start at the base, raise to the is equals the of. Okay, so if I rewrite this, that says 3 raised to the y, or to the something, gives me 1 over 27. Here's another important concept. Whenever you have a situation where you're taking the logarithm of a fraction, you want to try to rewrite that in exponential form with a negative exponent. So this is the same thing as 3 raised to the something is equal to 1 over 3 cubed. So notice I have now matched the base of my exponent, and I've turned it into an exponential expression of the same base, but it's still living in the denominator, and I need to get it up into the numerator so I can work with it. So to do that, I just make that exponent negative. So now this says 3 to the something equals 3 to the negative third power. Well, the only way I can raise 3 to a power and equal 3 to the negative third power is for that something to equal negative 3. Okay, over here that says 2 to the something equals 1/32. 2 to the something is equal to 1 over, that's 2 to the 5th. So you always want to try to turn into an exponential expression of the same base. And now if I bring that up, that says 2 to the something is equal to 2 to the negative 5th. So that something had to be negative 5. Okay, using the common logarithm, now we're getting into your calculator and what your calculator can do for you. All right, so sometimes you're going to see logarithms written without a base. So you're just going to see log of something, in this case, log of x. It is understood when you do not see a base written that that base is 10. So we call base 10 logarithms a common log or a common logarithm. So if you look at your calculator, you're going to have a button that says log on it, and it's not going to have a base. It is understood that that button on your calculator is operating in base 10. So that's nice for our Richter scale, since our Richter scale is also in base 10. And just an interesting side note, scales for measuring the brightness of stars or the pH of acids and bases is also on a logarithmic scale using common logs. So the important takeaway from this bit of notes, y equals log of x is equivalent to 10 raised to the y equals x because it's understood to be base 10. So when you're asked to evaluate the log of 1,000, basically you're being asked to figure out what can you raise 10 to give 1,000. 10 to the something is 1,000. That something had to be 3 because there are 3 zeros on the end there. And then over here on the right, understood 10, 10 to the something is equal to 1 million. 10 to the something equal to 1 million. With 1 million, I have 6 zeros, so that something had to be 6. Okay, so this little set of notes is telling you how to use your calculator, that log button on your calculator, the common log, understood to be base 10, and you just press log, and it opens a set of parentheses. You enter whatever value you're trying to take the log of, and then press enter. So if you look below, we have evaluate the log of 123. And I have hit my log button. It opened a set of parentheses. I'm going to type 123, close the parentheses, and hit enter. And when I get my solution here, I get that y is equal to 2.0899051111. And it says to round to 4 decimal places. So I'm rounding to this spot here. I look next door. It tells me to stay the same. So y is approximately 2.0899. In other words, that is the value that I would have to raise 10 to get 123. And if you think about it, that should make sense because 10 raised to the first power is 10. 10 squared is 100, not quite 123, but 10 cubed is 1,000. So if you were just estimating, you could probably guess that it's going to be closer to 2 than it is to 3. And we see here that it actually is. It's very close to 2. It's not even 2.1. So that's the value that you would have to raise 10 to. So I would have to raise 10 to approximately 2.0889, and that should give me 123. And when I put that into my calculator, if I put in 10 raised to the 2.0889, it's not going to be exact because I rounded the number, but I get 122.71566. It's very close to 123. Not exact because I did round. Okay, let's go back to our earthquake problem here. The amount of energy released from the earthquake was 500 times greater than the amount of energy released from the other. The equation 10 to the x equals 500 represents this situation where x is the difference in magnitude on the Richter scale. To the nearest thousandth, so that's 3 decimal places, what was the difference in magnitude? So I need to solve for x to find that difference. I'll change to logarithmic form. This basically says 10 to the what? What do I have to raise 10 to make 500? So to change into logarithmic form, that says log base 10 of 500 is x. But I don't normally write it that way. I would just write the log of 500, it's understood to be base 10, is equal to x. Now you can put that into your calculator. Log of 500 is approximately, I'm giving you approximate sign, 2.69, and it says 89, but I'm rounding, so 9, 2.699. Now let me remind you, let's go back and look at that very first graph. Here. Remember, we used the graph to estimate that same problem a moment ago. And we estimated graphically about 2.6 where those two functions met in their x's as an x value, 2.6. And so you can see why graphical is not as precise as calculating. It was close to 2.6, but it's actually closer to 2.7. But just using my human eyes, I wasn't able to see that much precision. That's why we have to have logarithms so that we can find the inverse of those exponential equations and solve. Okay, so we also have another key on our calculator, so another base that we can use with logarithms, and that's base E. And we were introduced to the number E in section 6.1 when we started talking about compounding continuously, compound interest, continuously compounded. So remember, it was that formula, 1 plus 1 over n to the n power as n approaches infinity. So your calculator also works in base E. And since E is called the natural base, logarithm base E is called the natural logarithm. We don't write log base E though. What you'll see instead is ln. So if you look directly below your log key on your calculator, you'll see the ln key. That's log base E. So its inverse, y equals the ln of x, its inverse is e raised to some power y is equal to x. So this is just another base that your calculator works in. Okay, so we can evaluate using that key. And our first example here is the ln of 500, so the natural log of 500. In other words, what can I raise? This is asking, what can I raise base E to make 500? So I'm just going to put the ln of 500 into my calculator, and I get that y is approximately, 4 decimal places is what we want to round to, 6.2146. Now, if I put the ln of negative 500 in, I get an error. It tells me non-real answer, because this is the same thing as log base E of negative 500. So this is asking, what can I raise E to make a negative number? E is a positive number. So there's no real number that I can raise E to get negative 500. Okay, and then I just put some extra practice on here because it does not hurt to practice as much as you can with these logarithms. So this first logarithm is asking, what can I raise 3 to make 1 over 27? I'm going to change this to log base 3 of 1 over 3 cubed. I'm going to bring that up, log base 3 of 3 to the negative 3rd power, and that equals negative 3. Because this is asking, what can I raise 3 to? Let me point this out. This is asking, what can I raise 3 to raise 3 to the negative 3rd power? Okay, log base 6 of the square root of 6. I'm going to change this to log base 6 of 6 to the 1/2 power. You never want to leave roots inside a logarithm. Just change it to exponential form. And now the question becomes very clear. What can I raise 6 to to raise 6 to the 1/2 power? And that answer is 1/2. Okay, so this first part on the next one, log base 2 of 1/8, and then I'm going to add 4 after that. So I'm going to rewrite this as log base 2 of 1 over, I can put that as a base 2 exponential expression, 2 cubed, and then I'm going to add 4. I need to bring that 2 cubed up, log base 2 of 2 to the -3rd power, and then plus 4. So just that first term is asking, what can I raise 2 to? To raise 2 to the -3rd power. And that part is -3, but then I'm adding 4 to get 1. Okay, 6 times the log base 8 of 4 and let's see, the square root of 4 is not 8. So what I have to do is figure out how in the heck can I relate 8 and 4. And this is a little tricky here. So here's what I do know. I know that the cube root of 64 is 4. And I know that 8 squared is 64. So I'm going to call 4 the cube root of 64. And I'm going to call now 64 8 squared. So 6 times log base 8, I'm going to run out of room for this one, of, I'll go ahead and change for the sake of space. I'm going to, in one step, I'm going to change 64 to 8 squared, and I'm going to, instead of the cube root, I'm going to change that, raising that to the 1/3 power. So 6 times log base 8, 8 squared raised to the 1/3 power. I multiply those exponents since I'm raising a power to another power. That gives me 2/3. So that is 8 to the 2/3 power. So now the question is, and I'm actually going to white out that last problem so that I have room to work the rest of this. And we just won't do that last problem together. Okay, so now I have 6 times log base 8 of 8 to the 2/3 power. So the logarithmic part of this is asking, what can I raise 8 to? Let me write this in. What can I raise 8 to raise 8 to the 2/3 power? That's just 2/3. So this is 6 times 2/3. And we multiply fractions straight across. That's 12/3, which is 4. Okay. So looking at these last 3, they're all common logs. I can actually use my calculator to evaluate these, or I can use my smarts to evaluate these. This is the same thing as log base 10, understood base 10. 1/1000th is the same thing as 1 over 1,000. That's the same thing as log understood base 10 of 1 over 10 cubed. I can bring that up 10 to the negative third power. Now the question is, what can I raise 10 to raise 10 to the negative third power? Well, that has to be negative 3. All right, and then I have log understood base 10 of 1 plus 7. What can I raise 10 to make 1? Well, the only value that I can raise anything besides 1 to get 1 out is 0. So this is 0 plus 7, which is just 7. And this last one, 2 times log understood base 10 of 100 to the negative third power. I want to put this in terms of 10 to have like bases. So this is the same thing as 10 squared raised to the negative third power. I'm raising a power to another power, so I multiply those exponents. This is 10 to the negative 6th power. So now the question is, what can I raise 10 to? To raise 10 to the negative 6th power, that is negative 6. 2 times negative 6 is negative 12. And finally, a word problem. The exposure index, EI, for a 35 millimeter camera is a measurement of the amount of light that hits the film. It is determined that by the equation EI equals log base 2 of F squared over T, where F is equal to the f-stop and T is the exposure time in seconds. If my f-stop setting is 8, so if my f is equal to 8, and my desired time exposure is 2, what will the resulting exposure index be? So I just need to plug in. I'm going to plug in 8 here and 2 here. So I get my exposure index is log base 2 of 8 squared over 2. And I'll go ahead and simplify that expression. That's 64 over 2, which is log base 2 of 32. I can rewrite 32 in exponential form of base 2. That's 2 to the 5th. And so the question now is, what can I raise base 2 to raise 2 to the 5th power? So I get my exposure index of 5. That's all I have for you on the basic understanding of a logarithmic function. I hope this was helpful.